All right. How's everybody doing today? Hopefully it's going well. This is Mr. Jenkins, and this is your fourth lesson of Chapter 3. It's called Linear Programming. So that's probably a new term. That we don't do any of that in Algebra 1. So we do some of the supporting skills, though. Okay. I'm going to let you guys kind of read about this stuff up here, but I will reference some of these vocabulary words that are defined up top. Basically, your learning target for this one would be that you can use technology to define the feasible region and its vertices. We need to be able to find the feasible region of a set of given constraints, which is basically a big system of equations. And then we need to figure out what its vertices are, or also known as corner points. All right, so anyways, here we go. First one we're going to do by hand. So this is like example 1, and we will just do this one old school with no technology. So example 1. This is an example of how to do one of these by hand. All right, make my page a little bigger here. It says, what point in the feasible region maximizes p for the objective function p equals 10x plus 15y? All right, so let's go ahead and try to figure that out. Okay, so first things first, we must kind of graph each constraint. All right, so like I said, this is like a big system of inequalities. All right, all this does right here, x is greater than or equal to 0, y is greater than or equal to 0. All that does is puts our graph in the first quadrant. If everything's positive, that just means we're looking at this part of the graph. So there's nothing we really need to do for that one because we were given a first quadrant graph. So really, we're worried about these two right here. All right, so these are nice standard form inequalities. So my x-intercept is going to be 16. So it goes through the point 16, comma 0. I think these graphs are 10 by 10. Let me make sure. 2, 4, 6, 8, or maybe 12. 6, 7, 8, 9, 10, 11. So yeah, 12 by 12. Anyways, we don't go out to 16. So let's go ahead and count by 2s. All right, so we'll do that. If you ever scale up your graph, you need to indicate that by just writing out the number. So this would be 2, so 4, 6, and then 8, and so on and so forth. Well, 16, 20. Sorry about the handwriting. We'll do the same thing here. Okay, now we're able to get these on the graph. Okay, so this one has x and y intercepts of 16. So it goes through, like I just said, 16, 0. It also goes through 0, 16. These are all going to have or equal to. Okay, so it's all going to be solid boundary lines. If it didn't, then the problems wouldn't make sense. I'll try to explain that as we go, why that's true. Notice I didn't put arrowheads on both sides because we're only looking in the first quadrant, so it wouldn't go past into the negative of x or y. It's just going to stay in the first quadrant. All right, and then as far as shading goes, it's less than, so we would shade on the low side of that line. All right, the other one, thinking about the intercepts, my x-intercept is going to be 60 over 3 is 20, so it goes through the point 20, comma 0. All right, and then 60 over 6 is going to be my the y coordinate of my y-intercept, which is 10. So it also goes through 0, comma 10. Right there. All right, it is also or equal to, so I'm going to choose a solid boundary line here. I believe it is also less than or equal to, so when it comes to shading, we shade on the low side. Of that one as well, so underneath it. So overall, you know, for the other two, you know, I'm shading above this line and to the right of this line. So where do we have all of our shading? So the answer to that is it's kind of maybe a little bit hard to tell, but if we're under and under these two, then it's going to be right here is going to be your shaded region. Okay, so right in there. All right, so that is what we call the feasible region right there. Now, the only reason we care about that is because we want to know what these vertices are, what the there's a corner point theorem there that says if an optimum value of the objective function exists, it will occur at one or more of the corner points. I like to refer to those as vertices, right? So if our shape of the feasible region is this, that's kind of all we care about, then where are the vertices would be the question. So that's anytime you have like a corner. That's why it's called the corner point theorem. So there's a little turn there, there, and there. All right, so it looks like we have 1, 2, 3, 4 vertices. All right, we already know that one is 0, 10. This one is, it looks like 12, 4. This one is 16, 0, and then we have 0, 0. So those are the vertices that we need to test, all right? And then all of that is to say we test them in this right here. So it's which point, and we want to know which one maximizes and which one minimizes. So we kind of have to sub them all in. I'm going to go pretty quick on this part. So let's just start here with 0, 0. So if x is 0 and y is 0, then p would be 10 times 0 plus 15 times 0, which is 0. All right. I'm going to run out of space here, so I'll do the rest of them kind of over here. So next one I'm checking is 0, 10. All right, so 0, 10, then P would equal 10 times 0 plus 15 times 10. So that would be 150. Then we're going to test 12, 4. So that'd be 10 times 12 plus 15 times 4. That's 120 plus 60, so that'd be 180. So that's our new leader in the clubhouse for the maximum value. So we do have one more to test, though. If we have, let's see, 16, 0. For 16, 0, that would be 10 times 16 plus 15 times 0. So 160. All right, so again, we want to know what's the maximum, what's the minimum. And at this point, we're just looking at the output values. All right, so we're just looking at the P values. So my smallest number is going to be, it looks like 0. All right, so that was one of my outputs was 0. So that's going to be my minimum. If we can get that highlighter to pull up here. 0 is my minimum and 180 is my maximum. All right, so you would want to just make sure you say which is which. The 180 is the max. Or another way to say that is the point 12, 4 maximizes it maximizes the objective function, and then the 0.00 minimizes the objective function. Okay, everything else in the middle would not maximize or minimize. All right, it would be somewhere in the middle. All right, so that's basically what we're doing. These would be pretty tough, without technology. So on most of them, we will use Desmos. All right, so that is what I would say is the meat and potatoes of the lesson, would be kind of using Desmos. All right, there is a trick to Desmos though. All right, so for these, I'm not going to put anything on my graph. I'm just going to look at it in Desmos. Okay. So just to save time, I've gone ahead and typed these in with one small difference. So we will talk about that once I pull it up. So I'm looking for example 1 here. There it is. If you haven't already done this, maybe signing up for your own account on Desmos is pretty nice to do because you can save graphs and stuff. All right, so anyways, it's all typed in, 5y plus 4x, and then is greater than or equal to 35, and then you can see they're all kind of the same. One note is that this one should say y is greater than or equal to 0, so that would be a typo. Y is greater than or equal to 0, or at least that's how I changed it. Okay, so what do you notice about all the inequality symbols, right? This one on the problem is less than or equal to, but I typed it in as greater than or equal to. This one was greater than or equal to, I typed it as less than or equal to. The reason that I do that is because if you type them in correctly, it kind of looks like the whole screen is shaded, and then you really have to think about where is my quadruple shaded region. It's kind of hard to tell. But if you flip around if you flip the inequality symbols backwards, then it makes your feasible region very obvious. It's the one region that doesn't have anything in it, right? So if we're making everything opposite, then that would mean that that's really the region where we have all the shading. It just makes it a lot easier to see, okay? So anyways, this is what it looks like. So how can I use this to find my vertices? Well, you want to kind of click on each kind of line there, if it'll let me, and it'll populate these intersection points, which is what we want. All right, so we can see easily that we have 0, 4, 0, 7, and like this line here, or one of them here. Trying to get this point. Yeah, there you go. And 5, 3. Right. So you can get it. You can get those points that quickly from Desmos. Okay. So again, and then from there, all you have to do is plug them into your calculator. So again, the vertices from the graph were 0, 4, 0, 7, and 5, 3. All right, so that's what you need Desmos for, coming up with those however many vertices. All right, and then from there, you just have to do the math. Okay, so our function here is this right here, p equals 8x plus 2y. So we will go ahead, given all these constraints, so we will go ahead and sub in our values and see which one maximizes. I think that's all it asks. Name all vertices, which we've done. Name the value of x and y that maximize or minimize the function. Okay, so let's see what 0, 4 does. So 8 times 0 plus 2 times 4 would be 8. 0, 7 would be 8 times 0 plus 2 times 7. That would be 14. Hopefully all this will pop up. Maybe I'll have to rewrite it. There we go. So we have 14 there, and then 5, 3. That's going to look like our winner for maximizing probably. 8 times 5 plus 2 times 3. So we have 40 plus 6, 46. All right, so here is our max value, 46. Here is our minimum value, 8. Right, so to officially answer the question, the point that maximizes, or we'll say the point that minimizes is 0, 0, and the point that maximizes is 5, 3. You got to be careful though on the test questions or on your Math Excel questions. It might ask you the maximum value. If it just said what's the maximum value, the answer would be 46. But on the wording of this one, it says what is the point that maximizes the value. So that makes the official answer the ordered pair, and the ordered pair that minimizes. All right, I'm going to save number 3 for you to look up on the notes. You might want to try it on your own and see if your answers match up. And then there is a word problem, which I'll go through to kind of finish these out. All right, so I'm going to go pretty quick just so this video is not too long. I know you guys can read all through that. So this is kind of a real world application. So again, kind of skipping to the good part here. You have to make your own constraints here. So that's one hard part of this problem. So try to read through and see how I came up with these constraints, because they're not directly given to you. All right, so the constraints of the problem are 24x plus 40y is less than or equal to 1,000. All right, another one is 48x plus 30y is less than or equal to 1,200. All right, I put one too many zeros on the other one. Sorry about all this delay, guys. And then you want to limit it to the first quadrant. Any real world problem, usually that's going to be the case. So we also have x greater than or equal to 0 and y greater than or equal to 0. So that's the extra step in the word problem, is you have to come up with the system of inequalities that represents the constraints. All right, so once you've done that, it's just the exact same kind of problem. So I'll go ahead and pull this up on Desmos. I titled this one Example 3. You can kind of see how they're all saving there. So it's pretty nice. Let's see, Example 3 is right there. And so there you go. So this is a good example too, where all this is going to kind of be off of your graph. So you're going to have to figure out how to use zoom and stuff. You'll have to zoom out on this one. You can also kind of move the graph around however you want it. So it's pretty cool. It's a very user-friendly website. All right. Anyways, we know at this point, all we need Desmos for is to figure out our vertices. So first of all, identify how many we have. 1, 2, 3, 4. All right, so if I click this line, I should be able to see these 0, 0, 0, 25. So that's 2 of the 4, and then the other 2 should be on this one. So 25, 0, and then 15, 16, right? So we have all our vertices. You saw how I found them. So Desmos really allows you to kind of work quickly through these. So once you've done that, then you just sub in your points and test them. Since I've already gone through how to do that. I'm just writing up the vertices here. hopefully they'll pop up, and I'm going to skip a little bit of the work again just to save a little bit of time. So once you know these, then you just identify your function rule. It's usually going to say something like P equals. Let's see, where is that? I'm trying to find it. This is the problem with skipping around here. Okay, so I guess it's this guy right here, 120x plus 90y. P equals 120x plus 90y. So that's our function, right? So that's what we're gonna multiply x values by 120, y values by 90. So in this one, that's gonna obviously give me 0. In this one, 25 times 90 is 2250. Here we have 15 times 120 plus 16 times 90. That's 3240. And then this one, we have 25 times 120, which is 3000. All right, so now we can easily see we're looking for the maximum profit here. So all we're looking for is the maximum profit. So that is, here's our winner. So we can say max profit is $3,240. That's the best we could possibly do. And then the combination that would give us that looks like 15 wall calendars with 16 pocket calendars. All right, so I'll wait for that to pop up, but that's basically it. I kind of went through this pretty quick, but your notes have this outlined pretty well. I suggest, you know, trying this on your own in Desmos. You got to figure out what you don't know because, you know, I won't answer those types of questions on test day. How do I use Desmos? Things like that. So get all that sorted out when we're working through the chapter and try to stay up on things because we're going through this one pretty quick. So anyways, hopefully this helps and you guys have a nice day. Thanks.